Hey, hello and welcome everyone. I hope you're all doing well. Good morning, good afternoon, good evening to wherever you are watching this all over the world. My name is Deep Jariwala. I'm going to be the host and moderator today. And we are very delighted and excited to welcome you all to the first edition of Youth Talks of ICANX. As all of you know, ICANX has been a vital and pivotal platform in enabling scientists from all over the world to share their exciting research over the past 2 to 2.5 years. As a result, it has gained a wide degree of popularity, and numerous scientists at all stages of their careers have deeply benefited from others sharing their from others sharing their research. So, what we have decided is to extend these ICANX talks to even younger scientists. And the reason being, younger scientists are the future of our society, and therefore, highlighting their research and promoting them via the ICANX platform is one of the best things we could do moving forward. And therefore, we're doing that. And so I will give you a little bit of introduction of how the youth talks, which are talked by younger scientists, are going to proceed over the coming weeks throughout the entire year. And then we have an exciting session of three young scientists today from various parts of the world who'll be sharing their research with you. And then we'll be having a very nice panel discussion discussing some of the issues surrounding young scientists and their careers, as well as the other technical topics that they bring up during their talks. Okay, so the Young Scientist Talks will be held every alternate Tuesday in English at 8 p.m. in Beijing time. I will be the moderator today, and then in subsequent weeks, you'll see other moderators as well. Uh, for the English, the talks will be held every alternate Tuesday in English, and for which I will be helping organizing or chairing. And then Professor Xin Huang from Tianjin University will be managing the Chinese program, which will be had every other Tuesday. And so for every Tuesday of the year, you will have either English or the Chinese version of this program. Okay. And so, as I was mentioned over here, there'll be total of 23 weeks of programs in Chinese, organized by a domestic committee in Chinese, and then 23 weeks in weeks in English. And the general plan would be we would have three speakers from very different countries. They will all be young scientists in the early stages of the career. They'll be giving 30 minutes talks and each, and then finally we will have a 30 minutes of panel discussion between all of them to sort of get a perspective of their science and their perspective on careers of young scientists. Okay, so here is the tentative calendar for the English talks. As you can see, today is the first talk over here. We are starting on Valentine's Day, so happy Valentine's Day, everyone, to all over the world. And then on February 21st will be the first the talk of the first use talk of the Chinese version, which would be next Tuesday. And then there will be many others which are being planned, as you can see. Not all of them are decided. Some of the sessions are decided, and as you can see, those moderator names have been placed over there. Okay. And so this schedule will be there all the way through the entire year. All of the Tuesdays will be covered all the way up to December 19th. Okay. So coming back to today's session, today we have a very exciting session. We have three excellent young scientists from three different parts of the world. We have Professor Ludovico Cademartiri from the University of Parma in Italy. And then we have Professor Zhuo from Fudan University in China. And then we have Professor David Dodoo-Arhin from the University of Ghana. And so I have a great pleasure of hosting all of the three today. And what we are going to do is we're going to start the program by starting with Professor Ludovico Cademartiri for his talk, and then we'll move on to Professor Zhuo and Professor followed by Professor Zhuo. We'll move on to Professor David Arhin, and finally we'll have a panel discussion. Okay. So with that said, let me get the first speaker online. We have Professor Ludovico Cademartiri from the University of Parma, Italy. And I will introduce the other speakers when their talk comes. First thing, what I would like to do is talk about, or at least introduce the title of Professor Cademartiri's talk, which is a very important title. The title is about addressing food supply security problem as a material scientist. And at that point, what I would like to request him to do is start sharing his screen, and I will provide a brief introduction to him while he starts sharing his screen. So, Ludovico, do you want to share your screen? Please give me a minute as I try to introduce you before we get
I'm sharing the screen right now.
Yeah, I think I can see your screen. It's a little bit slow on my computer. Yeah, okay. Welcome, Professor Ludovico Cademartiri. I should introduce him as our first speaker for this youth talk series. Professor Cademartiri obtained his bachelor's degree in material science from the University of Parma in 2002, and then a PhD in chemistry from the University of Toronto in 2008. He was a NSERC postdoctoral fellow in the group of Professor George Whitesides at Harvard University. His work is very interdisciplinary and spans materials chemistry, physical chemistry, molecular electronics, flame manipulation, plasma processing, environment by design. So, as you can see, it covers really a very broad area. And consequently, he's been recognized by many national and international awards. Most recently, the Beckman Young Investigator Award, which is a very prestigious early career award from the Beckman Foundation here in the USA, as well as the Plant Science Institute Faculty Fellow Award. He was at Iowa State University from 2012 all the way up to 2020, and is presently an associate professor at the University of Parma in the Department of Chemistry, Life Science, and Environment Sustainability. So, with that, let me hand over the floor to Professor Cademartiri. Please take it away. We look forward to your talk.
Thank you very much. Thank you very much. So, for the kind introduction and for the invitation to give this talk. So, I would have plenty of things to talk about, so I will get right to the meat. So, the thesis I will be proposing to you today is the following: that we are, in my opinion, at the onset of an epochal transformation of our society that is comparable maybe only to the Neolithic, and that it won't be driven as much by cities, but actually by countrysides, mountains, and forests. And that material scientists and chemists can be a key player in it, but that most likely not in the way that you think necessarily. So this talk is founded on the past 10 years of my work, where I've had the privilege to be working at the interface between material science and agronomy and plant science, and to work very closely with some of the best agronomists and plant scientists on the planet. So this is basically my conclusions that I've drawn on from this work. The food supply issue is an issue that is not as well known as it should be among the materials community, and is very pressing. The issue is that what is gathering on top of this, of the food supply, is basically a perfect storm kind of situation, where every single element of food production is coming on the US simultaneously. This is not, this situation is unprecedented in world history, and but as I will elaborate in this talk, it is also a time of unprecedented opportunity due to converging trends in technology, society, and science. So, for the sake of clarity, given the complexity of the food supply issue, I will try as much as possible to address the various problem areas, even though these are profoundly interlinked. So, the first problem area that affects food supply is, of course, logistics. Food production and the poor, we always have to remember the food supply means the lives of people, is heavily reliant on transportation of large amounts of mass, which can be water, seeds, produce, etc., over large distances to and from remote places. And so it relies very heavily on cheap fuel, roads, road maintenance, which are issues in many parts of the world. It relies on cold storage, so all the technology and energy that goes with it. And therefore, it relies on fuel, which is geographically clustered, and therefore, as we've seen, usable as blackmail due to political situations. Fertilizers are another ingredient. Of course, we're very reliant on fertilizers, especially mineral fertilizers, which are also geographically clusters. They are increasingly scarce. For example, look at the potassium shortages. It's extremely energy demanding to produce these fertilizers, especially the nitrogen fertilizers. About 1 to 2% of the worldwide energy production goes into the harvest process. It's very dangerous to store some of these fertilizers. Let's remember the tragedy of Beirut. And increasingly necessary and costly. So about 35% of operating cost of our average corn farm in the US goes into fertilizers. This is how much of a dent it makes. They leach profusely into the ecosystem because they're water soluble, causing all sorts of issues, not just at the environmental level, but at a public health level. And in principle, they would be replaceable. They could be replaceable in part or in total with organic fertilizers, which means animal and human manure. But this is very limited at this time by public health and cultural concerns mostly. So then we have pesticides and herbicides. These are substances on which we are very dependent on at this point, but they also have issues. They issues, of course, of the huge scale at which they must be applied, which means vulnerability to the cost of raw materials and energy. And they target organisms that, as we know now, they're capable of developing resistance even on the timeframes of a decade or two. And of course, these are bioactive substances that are deployed on a global scale with basically very, very little understanding on the ecological side effects, especially in soil, which is a notoriously opaque system. Climate change is another ingredient that is complicating our life dramatically when it comes to the primary sector. And in this case, what I want to stress is the effect that it can have on what is called in economics the concept of ruin. So the complete loss of an economic activity due to a single event. So climate change drastically increases the variability of weather, and with it, the probability of tail events, which can cause ruin for a farming operation. This, of course, affects much more the small farms, which don't have the diversity and the extension of the large farms. And by doing so, these increased weather extremes decrease the crop diversity, decrease the experimentation of better farming practices, which are often associated with small farms, and increase pests and weeds because of the changing temperature. The soil. Soil is another ingredient necessary for food production. And we are losing an amount of an extension of topsoil equivalent to the state of Michigan every year due to soil erosion. Soil erosion is due to a combination of intensive farming practices, land and water management, and of course it's worsened by climate change dramatically. So you see how interlinked all these aspects are. Water management is another issue. Water is the number one factor that determines the productivity of a crop. Of course, climate change changes the temperatures. With it, it changes evaporation, both from the soil and from the plants. Longer droughts mean soil fracturing, which make soil erosion much more damaging. And to make matters worse, agriculture already to this day accounts for about 70% of all freshwater use worldwide. So it would currently, this is not something that we can replace easily. It would take about half of the world's energy to produce that amount of water. with this by desalination with the current technology. So it's not something we can replace. Farming practices, though, or if you think about it, this is where we have the biggest opportunities, I think, because farming practices, from a fundamental point of view, they haven't really changed since we invented farming. Crops are largely planted in rows as monocultures. Actually, one can make the very valid argument, I think, that automation of farming has actually simplified farming practices, or better, it has actually simplified the fields, biologically speaking. So co-cultures and cover crops that used to be common have actually disappeared. The diversity of germplasm that existed has been drastically reduced. In fact, now, if we need diverse germplasm, where we need to go to places where farming is still done by hand and where this germplasm has been preserved. And while mechanization maximized farm acreage in flat lands, it has actually reduced farm acreage on hills, for example. Here in Italy has gained a lot of forest because farming on the Apennini has been abandoned since the use of tractor, because tractors are fundamentally incompatible with terraces or sloped terrain. Another point, and this is, we're getting to points that are extremely poorly understood by, especially by city people, is the aspect of economics of farming. So the most convincing data point that I can provide you is the fact that the fraction of the average salary be spent in food in the US has decreased from 17.5% in the 60s to only about 6.4% in 2015, while average salaries have barely kept the pace of inflation in the same period. So this effectively means that the primary sector is being choked. It's literally being choked to death because money is going somewhere else. And so this means that now margins are for farming operations are either razor thin or actually negative. And farms actually survive basically on subsidies, on national subsidies. So this means that if we think technologically about farming, we have to think that additive solutions, so solutions that require farmers to buy and deploy something additional, are exceedingly unlikely to be economically viable, exceedingly unlikely. So we come to breeding and genomics. So the food supply has been dependent on breeding and genomics, but as it turns out, the miracle of agronomists is that we have to this day a mean absolute increase in yield year over year. So we are constantly increasing the yield of our fields, but the relative increase year over year is actually decreasing. And this in spite of the fact that investments, but private investments by companies is actually skyrocketed. Not lastly, but maybe one of the most complicated problems is actually societal stigma against the primary sector. So food supply security is actually extremely dependent on human resources. This is well documented in history, but the primary sector is associated culturally in many places, in most of what we erroneously call the first world, with dirt, poverty, physical labor, smell, disease, and all sorts of negative connotations. The stigma is alive and well, also in the research community, and inevitably reduces the brain power that is devoted to these problems, and it affects inevitably the funding choices that are made by agencies. So this is an enormous problem that is cultural. I can give you an example of bias very briefly. So if I would tell you that I found a device that can fix CO2 using sunlight, and it takes that carbon and 1/3 of it stores it deep underground, and with the other 2/3, it actually creates with it very valuable construction material, that this construction material is biodegradable, and that when you're done with it, you can actually get energy out of it and purified water that has been collected underground. You would probably think that I'm certifiably insane. And yet, if I tell you that what I've talked about is a tree, you would probably think, well, we're not interested in that. We don't work with trees. And yet, we are very happy to spend billions of dollars in research on materials that can only do a very tiny fraction of what a tree does every day, every minute. So this is an example, in my view, of what is bias. So what can we do? Let's get to the meat. Or now that we've seen a scenario, what is the scenario? What can we do? Material science, of course, already contributes. It has been contributed to solving these issues for the past decades. For example, we have ceramic coatings in tools. We have UV-resistant polymers that enable drip irrigation. We have composites that enable drones. We have flexible semiconductors that are enabling sensors on plants. And we have biodegradable polymers that have enabled seed coatings. So every one of us has directly or indirectly contributed to solving the food supply crisis. But the issue that is now becoming evident is that there isn't really right now, as far as I'm concerned, a material that is urgently needed in agriculture that is not already available within a populated region of some ashby plot somewhere. So the question in general, when it comes to application of materials in farming, is not, do we have the material that can do this, but is it worth spending the money cost to buy and deploy it at such a scale? And do we know that it won't instead cause more trouble than it benefits? And the answer is generally no. So the issue is very different than what we're used to. So my first take-home message would be to kill your darlings, in quotes. Material science comes from metallurgy, and we have, therefore, a cultural tendency to add things. So we add things to make things better. And the problem with this approach, with this cultural approach, is that it's an issue of scale. So the arable land is about 10 to the 9 hectares. And just to produce a 1 ppm soil amendment to the top 10 centimeters of soil, it would require the production every year of about 1.5 kilometers cubed of material. So this becomes a little bit tricky. The second problem is more deep, more profound, and it's that the entropy of mixing is always positive. It's always large and positive. Therefore, when you add something to a system, that operation is generally irreversible. And the complexity of this ecosystem means that when you add something to it, second-order effects that are unpredictable are bound to happen. So this is a very bad combination. This is a very bad combination. So then the question that comes obvious is, if we shouldn't add anything, then what can we do? What is something, and this is the question that I have for you, what is something that you can always add, in quotes, to a complex system without increasing its entropy, while improving actually its predictability, its performance? And my take on this is that what you can always add is information, it's knowledge, it's know-how. That's what we actually desperately need. And so how? My take on this is that using the materials know-how we have to provide or help provide otherwise inaccessible information to the agronomist, the plant scientist, the soil scientist. So to help the generation of know-how, because this know-how will then enable the simplification, the sustainability, the diversity of solutions that can leverage new technologies like AI and robotics. So where now that I've said we need to generate knowledge, then the question is where? Where do we need this knowledge? And my take on this is that probably the plant soil system is where we have the biggest unknowns. And the reason why it's so important is because it's unlikely that we're going to substitute plants grown in soil with anything else in terms of calorie production. It is, especially for roots in their development, the questions that we have are extremely basic. We really know extremely little about a lot of what happens in soil. And so it doesn't require a sophisticated understanding of biology to make a contribution. Thirdly, plant biology has very advanced characterization tools, but the tools that actually are used to grow organisms haven't really changed in 50 years. We still use Petri dishes. So it's basically like doing chemistry before the invention of glassware. So it's huge opportunities there in terms of tool generation. And plants are not too big to be subject of experimental work in chemistry, physics, or engineering laboratories. We do it in our laboratories. And soil is effectively a porous material. And we are the top dogs when it comes to porous materials. We know better than anyone how to create them, characterize them, and understand them. So this is why I think plants and soil should be the focus of our attention. Now, I'll give you 3 examples now in the last half of my talk from the work of my laboratories. One is in hydrogen-based transparent soil. One is millifluidic Lego-based programmable ecosystems. And the last one is paper microfluidics that are used to quantitatively study hydrotropism. I will very briefly, tell you why we did it and what were the conclusions. You can get the details on the papers. So the first one was about making transparent soil from hydrogels. And the reason for this was that it's very important for us to be able to monitor root development in vivo. And the reason for this is that we need to understand root development adaptation under stress, how plants adapt to stress and adapt the root development to it, and how to correlate gene expression to root development. Now, what is the problem? What is the problem from a material standpoint? Then roots require access to oxygen. This is something that a lot of people don't know. And the crops, of course, grow naturally. So physiologically, crops grow in soil, which is an heterogeneous system that is composed of solid, liquid, and air. Now, the issue is that heterogeneous systems are opaque unless they're index matched. But the issue is that you cannot index match air to the material. So how can you do it? So what we decided to do, we created a gel and gum agarose spherified hydrogel that is cross-linked with magnesium that is actually index matched to plant nutrient solutions. So what we do with this, we can create arrays of these beads that have pores filled with air inside, and that when they are saturated with nutrient solution, they become transparent and they allow, for the time being, the imaging of the root system. So you can grow the plant in the drained system, and then when you need to take a picture, you saturate it with nutrient solution, you take a picture, and then you drain it. And this allowed us to get a very clear in vivo imaging of the roots. These are plants of soybean. And what you see in the top row is the plant grown in hydroponics over the course of a week. And in the bottom row is the same soybean plant grown instead in transparent soil. And you can see the drastic difference in root development that occurs. And of course, there are much more details about the phenotyping of these two systems in the paper. But what we found also is that the gene expression indicated no stress from waterlogging in the plant grown in transparent soil. This tool, this medium, allows also for microscopy on live Arabidopsis thaliana roots in Petri dishes. And also, because it's a material that you can fully control, and it's a medium that you can fully control, you can go and study and implement gradients, for example, water potential or nutrient concentrations, and study quantitatively tropisms. So tropisms means the tendency of a root to grow somewhere in some directions along some gradients. And so here you see, for example, a plant of a root of soybean that is growing towards higher water potentials that have been generated and deliberately created inside this transparent soil. The next example from my work is millifluidic Lego-based programmable ecosystems. Now, why do we need programmable ecosystems? So it is very important to create model ecosystems with which to study quantitatively the chemical interactions that occur between organisms. And by this, I mean microorganisms and microorganisms in plants and plants with other plants. So where is the problem from a technical point of view? The problem is that cultivated microorganisms tend to occupy all the space that is provided to them. Typical interaction, though, that happen at the millimeter scale because of the diffusion bottleneck. So diffusion is extremely slow, and so what happens is that viable chemical interactions require basically contact. The problem is that roots, though, are instead centimeter scale. So which means that for organisms, if I want to have plants and microorganisms interact, I have to, nowadays, make them grow in the same environment. But this basically prohibits quantitative analysis of what is going on. I can't separate the two organisms and quantify the kinetics of interaction. So what we did was to create modular, reusable, sterile, air and watertight environments for organismal growth. So what you see here is microorganisms and plants that are based on Lego bricks. Transparent Lego bricks are made of polycarbonate, so it's autoclavable. These environments are connectable in a modular fashion through valves and devices that allow you to control exactly what is being exchanged between the nodes of this network, so between each organism. Now, the issue is, of course, is that if you see these networks, the organisms are separated, as you can see, by many centimeters. If we allow just diffusion to take place, these organisms will never interact chemically because they're too far apart. So what we found and implemented was that if you oscillate the fluid inside these networks using an Arduino-controlled $10 peristaltic pump, this creates actually a mass transport in the network that is thickened. So it's effectively you can model it as diffusion, but where diffusion can be, where this mass transport can be controlled in its kinetics. So effectively, I can grow organisms that are physically separated by 10 centimeters, but that will chemically interact as if they would be effectively in contact. And so this is what I mean here by effective distances. So that's the distance of chemical interaction. And using this fluid dynamic tricks, we basically showed how we could connect chemically Brassica rapa plants to colonies of Bacillus megatherium, that were physically separated by 10 centimeters, but we could make them interact as if they would be 1 millimeter apart as they interact, for example, in the rhizosphere. So effectively, this tool allows you to section the rhizosphere. The third tool that I'll present to you, the third example of contribution to plant science is by using paper microfluidics to study hydrotropism, so the tendency of roots to grow towards water. And it's very important to understand how roots seek water because, of course, of the growing drought issues. So what is the problem to do that from a technical standpoint? From a technical standpoint, water seeking for hydrotropism is assumed to follow a water potential gradient, and we know that it does in many conditions. But there is a little bit of an issue with this assumption. The two issues are the following, that in most circumstances, in most soils, the gas phase inside soil is close to 100% humidity. So there isn't much gradients there in the water vapor concentration. And secondly, in all circumstances, the surface of roots is covered in a layer of water because it's hydrophilic. And all hydrophilic surfaces are covered in water in normal humidities. Fourth, and this is a technical problem, it is very difficult to monitor the development of an entire root system in contact with an arbitrary and constant spatial distribution of water. I'll give you an example of what we did. We created a setup that allows to grow an entire root system on an arbitrarily defined distribution of liquid water by using paper microfluidics, but using it differently than what is usually than how it's usually used. So I'll give you this example. So if you have a nutrient solution and you put a paper pad at the surface of it, you could grow a root on top of it and use capillarity inside the paper pad to drive the nutrient solution to the root, right? This is pretty standard fare. But if I actually print that paper pad with wax and melt that wax through the paper, that wax is hydrophobic, so it prevents capillarity from doing its job. Now I have that those black areas that I printed with wax will remain dry, while capillarity will work everywhere else. So this means that I can, with a normal printer, I can print distribution, an arbitrary distribution of water sources in contact with the root system. And this is how the system looked. So it's just a sheet of paper that has been printed with wax, and the root system is growing on top of it, which allows me to monitor in real time what happens and in which direction the root grows. Our simulations, furthermore, show that the root tip, which is what in theory should be sensing the water, when the root tip is on a dry patch, the gradients of water vapor concentration to which it's exposed are extremely small. So we're talking about 10 to the minus 4 millimolar per meter. So it's very hard to understand how the root could find water once it's exposed to this kind of gradients in water concentration. And yet, when we did our experiments, with progressively smaller concentration of water. So where these areas filled with water would be more and more rare, we found that as the water becomes more and more rare, so the more stressed the plant is, the higher was the chance of finding roots on top of the water. So somehow, even though the roots were not exposed to a significant gradient of water potential, the roots were still seeking and finding water. And so the question now is to try to understand what is going on. How does a root system is able to sense something that it cannot sense, or whether the plants are actually that sensitive to water potential. So in conclusion, there are tremendous opportunities here. Use creatively our material science know-how to help agronomists, plant scientists, soil scientists, and microbiologists to generate knowledge on the ecosystem we live in. And as knowledge accumulates, in my opinion, it can be fed then to AI models or to humans to help simplify and integrate the production of food, water, energy from our rural ecosystems by taking advantage of developments, for example, in robotics and energy harvesting. And this information-driven integration, in my opinion, is the only thing that could help reduce environmental impact of the primary sector while improving the economic bottom line, which is urgently needed. And with this, I am done. And I thank you for your attention. Thank you very much.
Okay. Thank you, Professor Cademartiri, for that very inspiring and amazing talk. It was really a great exposure of the use of material science in agriculture and plant growth. And there is so much fundamentals to learn and so much exciting science to learn across, at the connection of these two disciplines. Personally, I'm more of a inorganic material scientist, so I had never thought there were so many interesting connections to be made of optics, photonics, as well as the chemical transport at the intersection of these disciplines. So thank you once again. So we move on to our next speaker. The next speaker is Professor Zhuo Li from Fudan University in China, and her talk will also focus on a slightly different topic, but more on materials again. But this time on flexible hybrid electronics, comprising both of materials and process design. But before she gets started, let me provide a brief introduction to her. So Professor Li is an associate professor in the Department of Material Science at Fudan University Her research interests, again, are very broad and diverse, including functional polymer composites for electronic packaging, as well as stretchable electronics. She received her bachelor's degree from Tongji University and her master's degree from Virginia Tech, and then her PhD from Georgia Tech. Before joining Fudan University, she worked as a materials engineer at Celanese Corporation and CNPC in USA. She has been the recipient of several prestigious awards. I won't list all of them since we will run out of time, but I will mention a few of them, namely the Shanghai Pujang program in 2017, the Rising Star program in 2020 from the city of Shanghai, as well as the IEEE EPS Outstanding Young Engineer Award. She has published many papers in many prestigious journals, such as Nature Communications, Advanced Materials, and so on. She was also very active in service and of the scientific community, and serves as the guest editor for IEEE PMT, as well as on technical committees of the IEEE ECTC, and co-president of IEEE EPS Shanghai, as well as vice president for IEEE Women in Engineering in Shanghai. So with that brief introduction, let me hand over the stage to Professor Lee, who will talk to us about materials and process design for flexible hybrid electronics. Professor Lee, the stage is yours.
Okay, thank you. Okay, happy Valentine's Day, everyone. I think it's my pleasure to present our work in the first volume of the Youth Talk and in this special day. And I'm going to briefly introduce our work on the materials and processes design in flexible hybrid electronics, or what we call FHEs. And my talk will be divided into 5 parts. Firstly, the background, and then I will talk about the stretchable interconnects, the substrates and sensors for FHEs, and the conclusion and the acknowledgement. So the past 2 decades, we have witnessed the fast development of electronics, from the bulky and slow computers to the lightweight, thin, and smart PCs, pads, and cell phones. What will be the trend for the electronics in the next 2 decades? So I think one of the trends is the connections and communications of all the things, including human beings. Therefore, we need all kinds of wearable devices. But considering the low modulus of and the elasticity of the biological components, we need to fabricate soft and stretchable systems to ensure that when we wear it, it's safe and comfortable. There are basically 3 different fabrication strategies for the current stretchable electronics. The first one is still using the conventional inorganic materials and making them extremely thin so that we can bend them and into different wavy structures that can be stretched. But this makes the design and fabrication of devices very complicated and costly. The second one is developing functional polymer materials such as dielectrics and semiconductors that can meet the electrical requirements and can still be stretchable. Although great progress has been made in the past decade, the performance and the stability of these organic materials are still far behind the inorganic counterparts. And the third one is the topic today, or what we call the flexible hybrid electronics, where the conventional silicon chips and the passive components are surface mounted on a stretchable substrate and connected with stretchable interconnects. So this method leverages the advantage of conventional ICs, such as high computational performance and communication standards, with the merits of printed electronics that allows massive production and high stretchability. Nevertheless, the FHEs have imposes very high standards for the materials used in the system. For example, for the stretchable interconnects, we need it to be very highly conductive, just comparable to metals, very good stretchability, and also good adhesion with both the components surface mounted and also the substrate and also ideally a high IO density. And for stretchable substrate, we need it to be stretchable, of course, and if they are used on skin, we want it to adhere reversibly on the skin and have certain breathability to give us the comfort. And for the stretchable sensors, we need it not only be able to be integrated with the FHE system, but also meet the sensing requirements, such as high sensitivity and high precision. So in this talk, I will discuss the progress in our group with respect to these three areas. First, I will talk about the stretchable interconnects. Currently, the majority of the FHEs are still using metal interconnects. They make it wavy structure, and so that they can be stretched. They have very good conductivity, and they have very mature bonding technology, just as in the common electronics. But the fabrication is costly, and the wavy structure limits the IO density, and also they are not printable. So therefore, in our study, our objective is to develop another kind of interconnects, that is the stretchable electrically conductive adhesives, or what we call the SECAs, that is printable to enable very fabrication, and the intrinsic stretchability eliminates the necessity to make it to make a wavy structure, and therefore we can increase the IO density. And also because of the printability, it can increase the integration density, but on the other hand, they have inferior conductivity and bonding strength compared to metals. So if we want to use this SECAs, basically it's a composite material, then we need to increase the conductivity and the bonding strength. And because most of the stretchable electronics use polydimethyl siloxane, which is called PDMS, which is a silicon rubber materials as a substrate. So we use PDMS as a polymer matrix for our SECAs, and the silver microflakes, which is the most conducting metal, as our fillers. So the prepared composites are soft and stretchable, just as common rubbers. However, if you directly mixing the commercially available silver flakes with PDMS, you will probably only get a highly resistive or sometimes even insulating composites, even when the filler loading reaches 80 or 90 weight%. So what happened? Why we did not get a high conductive composite? So in the first step, we studied the interface between the silver flakes and the PDMS matrix. What we find is that this results from the lubricant of the silver flakes. Commercial silver flakes are coated with a thin layer of long chain carboxylate group that can coordinate with the silver flake surfaces. Despite of the usefulness in processability, their insulating nature of this layer impede the electrical performance of the SECAs. As the carboxylate is easy to be reduced to silver nanoparticles. Therefore, we propose to add some mild reducing agent, in situ reduce the lubricant to form silver nanoparticles. It has several advantages. First, it does not require additional materials and processes while achieving a high conductivity. Secondly, the formed nanoparticles are from the silver surfactants, so they are on the surface of silver flakes. So it's easier for them to form conductive pathways. Thirdly, the lubricant remains during mixing and removed during curing. So that means it enhances the conductivity while not affecting the processability. Of course, the removal of a lubricant can reduce the contact resistance and therefore reduce the resistivity. And during the curing of the PDMS, it promotes sintering between the flakes and further reduces the resistivity. Therefore, we can reduce the resistivity all the way to 10 to the minus 4 ohm centimeter, which is already close to the conductivity of metals. Later, we also find that another way can do the similar thing is to halodize the silver carboxylate to silver iodide or silver bromide first, which are very photosensitive and can be reduced to silver nanoparticles after exposure to sunlight, which can again go through the sintering process and form a highly conductive composite. So after solving the conductivity issue, another important parameter for the interconnects is the adhesion. So for PDMS-based SECAs, it can bond with PDMS substrate because basically they are the same thing. So through the chain interpenetration, so their interface is very stable. However, on the top surface, when we surface mount those components and chips on the substrate, it has relatively weak adhesion with the metal pins of those chips and the components because of the inertness and the no surface energy of PDMS. So a conventional way is to introduce some coupling agents, shown as green here, which can react both with the PDMS chains and the hydroxyl groups on the copper surface. However, their adhesion strength is usually no more than 1 megapascal. This is because those coupling agents may not be evenly distributed on the surface, and no other energy dissipation mechanisms is introduced in the interface during the crack propagation process. So here we proposed another strategy. We introduce 10% of polyborosiloxane, PBS, into the PDMS chain and forms a PBS and PDMS double network. This PBS is formed with hydroxyl-terminated PDMS and boric acid. So they condensate to form multiple reversible cross-links, and it can form homogeneous structure with PDMS chains because basically their chain structure are very similar. And those reversible bonds can bond with the hydroxyl groups on the metal surface, and the styramic bonds exist in the bulk, can serve as a energy dissipation source during the crack propagation. So because of these three advantages, what we get is for the pure PDMS polymer, we can achieve a high adhesion strength to 6 megapascal, which is almost 6 times compared to that of the pure PDMS. And also, we can get 3 times of the styrene, which is a common coupling agent for copper bonding with PDMS. And its conductive composite, the SECA, can reach an adhesion of 2.9 megapascal, which is 8 times of the original SECAs without any treatment, and still remains the high conductivity as the original ones. And when we look at the finer mode of the lab shear test of our pure PDMS and the silane coupling agent treated ones and the PBS double network treated ones, we find that the fracture surface of the current strategy is not only 100% cohesive thinner, that means it has very strong adhesion on the copper surface, but also it exhibits a very unique ductile fracture, which means that it's a ductile fracture surface means that it triggers some energy dissipation during correcting, which will dramatically increase the fracture energy and increase the lab shear strength. And we used this double network SECAs in building a temperature sensor FHE circuit and test its stability during the mechanical deformation. The sensing mechanism of the sensor is that the pulse width will decrease with increasing the temperature. As you can see here, the performance of the stretchable sensor is equivalent with our PCB, the conventional hardboard-based sensors in the sensing performance. But more importantly, it can sustain during bending, during twisting, and even after we elongate it for 70%. As mentioned earlier, the PDMS SECAs also have the unique advantages of printability. By screen printing, we can fabricate lines as narrow as 200 microns and with a flat surface. And recently, we also developed a formulation that can allow direct writing of such printing inks. And because of the printability, we also enable the multi-layer structure through stretchable and conductive via holes. So we use a PET board to flatten and protect the PDMS substrate, and we laser cutting via holes. Then we can fill the via holes with our SECAs and print the circuit on it. With the classical stencil printing process and the surface mounting of the components and chips, we can build multiple layers of this structure, which can increase the function and the integration density of the obtained electronics. With these capabilities, we demonstrate a electrocardiology sensor and a acceleration sensor package. So it includes several modules, as you can see here, and we can integrate it with the SECAs and the wheel holes that we introduced just now to enable multiple structure. It is small, it is thin and flexible because of the high integration density, and it can wirelessly capture and transmit the data to the cell phones. The high adhesion and the strain isolation strategy enables stable performance during deformation. It has equivalent performance with the commercial electrode, as you can see here, and the data acquisition cards, and with even slightly better signal to noise ratio. But because of the stretchability, the softness, and the small size, and net weight, and wireless feature, so it can provide a better wearing comfort. I think this one can be applied for the health and motion monitoring for sports lovers and the elderly. And the stretchable substrate is another essential component for the FHE system. Besides the common requirement of stretchability, when it is applied on the skin, it has other requirements. For example, we want it to be sticky to the skin so that it will not detach or affect the stability during human motion. Also, we want it to be as soft as the human skin to make it comfortable. However, on the other hand, when we surface mount or integrate the IC chips or a component on the surface, we also want it to be hard and creep resistance so that the component will not fall off or delaminate from the surface. How could we meet these seemingly contradictory needs in one substrate? So we learned it from nature. Biological materials often exhibit mutually exclusive properties in one system. For example, our bones and the antennas in deers, they have a gradient in porosity, so they can resist the fracture and have a low density at the same time. Likewise, for the plant bamboo, it has a gradient distribution of fiber density in the same manner to enhance the resistance to the external load. And inspired by these gradient structures, we designed a PDMS with cross-linking density gradient, as you can see from the modulus mapping from in the depth direction, we can see a modulus difference from very soft and tacky to very hard PDMS. So what we obtain is, on one side, it has a low cross-linking density, so it can form soft and adhesive interface with the skin. And the adhesion strength can be even higher than the Scotch tape that we use daily. And on the other side, we have a very high cross-linking density. So it's hard, it's strong, and it maintains the mechanical robustness of PDMS to support the integration of ICs. So it can both have enough adhesion without sacrificing the mechanical properties, such as the modulus or the tensile strength. In addition, for on-skin electronics, another issue is the accumulated sweat in hot and humid weathers at the skin interface. This will compromise the comfortness, the reliability, and the fidelity for the long-term monitoring. So most of the previous work would introduce some process structure so it can enhance the evaporation and make it breathable. But these perspiration removal measures are still relying on the natural evaporation rather than the active absorption of the sweat. So again, we learn from nature that the plants usually has the vascular structure. It uses the hierarchy pulse structure to achieve the anti-gravity water transport from the soil to the plant, stems, and leaves. So here, inspired by this phenomenon, we designed a gold and thermoplastic polyurethane and a cellulose membrane system that can pump the sweat from the interface immediately through the combination of gradient in porosity from micron to submicron nano, and the surface energy from superhydrophobicity to hydrophobicity and superhydrophilicity. And in this design, because of the dual gradient in porosity and surface energy gradient, so the sweat can penetrate from the silver and the TPU side into the cellulose membrane side and spread. But the outside water, such as rain, will only spread on the cellulose membrane side only, and it will not penetrate to the skin. So in use, it can provide us both a high water transmission rate and a high water evaporation rate. And for the IoT system, sensors are another important part and a basic building block. So here we will also introduce some of our recent progress in the one of the most commonly used stretchable sensors. That is the pressure sensors. So for sensors, usually we are concerned with its high sensitivity. So to have a high sensitivity and the ability to be integrated into the PDMS-based flexible hybrid electronic system. So in our first work, we embodied the ultraline-like hollow carbon spheres into the PDMS matrix and obtained a highly sensitive sensor based on the phentolenane mechanism. So the spiky structure is able to concentrate the electrical field to the very tip of these spheres, and thus, if without a pressure, it is insulating. But with a tiny pressure, the small distance change between the spheres can trigger a large current change for the sensor. So that's why we can obtain a high sensitivity. Because of the submicron size and the ultra low concentration of these spheres, the transparency is as high as 87%, and the high transparency and the print-up capability is able to help us to fabricate an invisible single-point sensor that is 5 micron by 5 microns in size and is almost invisible. And this sensor can let's see. can detect a very small pressure, such as the falling of a feather. And also, because of the printability, sorry, because of the printability, it can be printed into a high density of 64 by 64 sensor arrays to detect the shape of an object, such as the shape of the legs of a toy ant, and the motion of a moving body. For example, if we put a ball on it, it can detect the motion, track the changes of the ball. Besides the sensitivity, precision is another important parameter for sensors. However, the current pressure sensors with high sensitivity usually have a relatively low precision. This is because they rely on complex structures such as composites and micro nanostructures. This complexity will increase the random error and thus decrease the precision. So here we propose to introduce the field emission structure to solve this problem. Here PDMS is used again as the sensing layer, while the vertically aligned carbon nanotubes embedded in epoxy resin is used as the emission layer. The former is a pure polymer, so it can minimize the random error and maximize the precision. And while the latter can provide a high sensitivity by the tunneling effect. So here, as we can see, we can obtain a high sensitivity that is comparable to the very best values currently, and also the variations between different measurements is as small as 1.6%. Also, it can have a very fast response within 4 milliseconds. So in conclusion, we present a FHE system that is basically based on the polymer composite materials. So for the stretchable interconnects, we produced the SECAs, which is basically a silver and PDMS-based composite. It has a high conductivity, good adhesion, and printability. And for the substrate, we designed the PDMS with cross-linking density gradient, which have good adhesion to the skin and mechanically robust to support the component integration. And we designed the breathable and sweat removable substrate with both porosity and surface energy gradient. And then we also fabricate some stretchable pressure sensors that has high sensitivity and density, as well as high sensitivity and precision. So in the future, we are seeking to increase the resolution and decrease the line width and line distance, further increase the IO density and support other packaging methods. And we also want to try other functional circuits. Finally, I would like to acknowledge the hard work of my students and also the collaborations from Professor Li Mingwu and Professor Ya Jieqing from Fudan University and Professor Hao Wu from Huazhong University of Science Technology. And we also appreciate the financial support from these agencies. And thank you very much to spend the very valuable time with me today. Thank you.
Okay. Thank you, Professor Lee, for that very nice and interesting talk. It was quite illuminating how far flexible and stretchable electronics and printing has come. I used to read these topics when I was a PhD student, and at that time they were just starting out. And in several years since, it seems like your group and various others across the world have come really far in this research area. So it's very, very nice to see that. Then we can now move on to our third presenter. The third presenter has his talk also focused on materials, but this time the focus is more on energy materials. And so before I hand over the stage to him, let me give a brief biography of the presenter. So the presenter is Professor David Dodoo-Arhin. He's a full professor of material science and engineering and also the director of the Institute of Applied Science and Technology at the University of Ghana in Africa. He obtained his PhD degree in materials engineering from uh, the University of Trento, Italy, in 2010, with a focus on nanostructured oxides for energy and environmental applications. He then undertook postdoctoral research fellowships and visits at various universities, University of Pretoria, the Cambridge Graphene Center at University of Cambridge, the University of Strathclyde, also in the UK, University of Poitiers in France, and then also in Germany. So he has been all over the place, from Africa to Europe, and then he returned back to Africa to start his independent career. He's had many honors to his name. I again won't list all of them because we don't have enough time. But he's a fellow of the Africa Science Leadership Program, which is very prestigious program, and it aims to grow early to mid career African academics in terms of thought leadership, team management, and research development. He's also a fellow of the Inter Academy Partnership Science Advice Science Advice for Policy at the International Network of International Science Council Regional Office for Africa. Uh, he has served again the academic community in various ways, namely on the Danida Fellowships, a national screening committee in Ghana, the screening panel for future leaders of the African Independent Research Fellowship Program, known as FLAIR. Also been the steering committee chairman of the African Academy of Sciences, RISE postdoctoral fellowship program. So he's truly contributed towards the development and uplifting of early career researchers all over the world, but particularly in Africa over the years. He's also a member of several professional bodies. He has many publications to his name, more than 90 in very prestigious, in extremely prestigious journals all over the world. 5 book chapters as well as 1 patent. And so, with that, let me hand over the stage to Professor David Dodoo-Arhin, and his title today is Engineered Carbon-Based Technologies: The Energy Materials Perspective. David, please take it away.
Hey, thank you very much for inviting me, and privileged to speak with you here. My topic is, as has been described, with dealing with the carbon-based technologies. But before then, where am I coming from? This is where I'm coming from, Ghana here. If you've never been, there's an opportunity for you to be here. I like this picture very much, that you can enjoy the beautiful part of the country. What is the role that you can do? There is a privilege that has been given here by we selected to organize the 17th International Conference on Advanced Materials. That will be an opportunity for you to be in Ghana, which is going to happen in December of 2025. So we still have time for you to prepare. I'm coming to you from the University of Ghana, which was established in 1948. We have over 68,000 students, and we work in so many different areas. My research includes the nanostructured materials and carbon materials and crystallography, among others, for collaborative purposes. Today, my talk is looking at some of the dimensionality that we can look at carbon. Carbon materials, as we have already known, have different dimensions. We can look at it in terms of 3D carbon. We can look at 2D carbon. We can look at 1D and then 0D. We know from diamonds, we know from graphite, which are 3D, which were known about more than 3,000 years ago. Then quite recently came with the graphene, which happened in 2004 at Manchester when the Nobel Prize was awarded. There were a lot of research in that area. We can look at carbon nanotubes and look at fullerenes. But my talk today is going to be based on graphene. which I did in 2 different postdocs in 2 different collaborations in University of Pretoria and in University of Cambridge in the Cambridge Graphene Center. We know a lot about this material called graphene, where it is an allotrope of carbon with a planar sheet of carbon atoms, which are arranged in a hexagonal network. And there are several properties. Because of those properties, we can use them for several applications. They have been known to have zero band gap semiconductor. They have massless particle near decay. And we can see all these various properties and some applications that we can use. When we look at carbon, we can think about it from graphite perspective, and we can look at it as a structure of graphite, which we can also look at the graphene as a book and looking at them as sheets of papers within the book. So we can actually peel this material from graphite and get our graphene, which are the sheets of the atomic level sheets that we can find, for instance, in the book. Because of this, it has several properties, including optical transmittance, which means that it can be used as a transparent conductor. There's reflectivity of it. It can be doped. When it's doped, we can get approximately about 60 ohm per square, which means that it is conducting. Based on that, we can also use it as metal mesh with about 4 ohm per square at about 80% of transmittance. It is also flexible, so we can find applications in strain measurement. We can also apply them in nonlinear ultra-fast optical response, like in the saturable absorbers. We also look at based on the optically wideband that they have, they can be applied also in linear dispersion of Dirac electrons. Here we find so many applications that we can put our graphene in, and it includes biosensors in solar cells, electronics, smart electronics, energy storage. Our interest here is in the photovoltaics and also in the case of energy storage in supercapacitors. What do we do here in our case? We know that graphene, because of this properties, can be used as transparent conductors because it can cover even within the visible range. Based on that, it can be used as metal grades, or we can use the metal nanowires, can use metal oxides, and these ones have been explored as alternative material to ITO in electronics. What then do we see in graphene as transparent conductor? When we look at its transmittance, it can cover from 250 nanometers up to even the stretchable from 2000 nanometers onwards. This means that this material is a good material that we can put in several applications, including photovoltaics, where the graphene can fulfill multiple functions in these photovoltaic devices. We have already seen that we can use it as transparent conductor window. We can use it as a photoactive material. We can use as a channel of charge transport. Can be used also as a catalyst. When we go to solar cells, silicon-based solar cells, explorations have been used for graphene being used as a transparent conductive film as a window electrode in inorganic solar cells. In organic solar cells, we can also find several applications, including that of a photoactive material, transparent conductor, and theoretically, it has over 12% that should be possible using this material. We have also tried to explore the use of it in dye-sensitized solar cells, and we find that the graphene can cover even larger number of functions in DSCs, including the graphene transparent conductive films that are used as window materials for all these various applications, including the graphene being incorporated even into nanostructured materials like TiO2 photoanode that can be used to even enhance transport rates. This is very good, and in our case, we have explored the use of this graphene based on its specific surface area and used it as a replacement for platinum in the case of dye-sensitized solar cells. We can also explore in supercapacitor for energy storage purposes because of its same surface area and then good electrical conductivity. It has found these applications. It's been known that it has a high tendency of reactivity of the ions, which usually towards the graphene oxides or graphene metal composite sheets than in the case of pure ones. So we can find several applications, and it can produce even more higher capacity than in the case of the pure graphene. We explore here means of producing large-scale graphene, which can be used for several applications. These include liquid phase exfoliation, would use chemical vapor deposition. We could also look at the mechanical exfoliation that was one of the beginning for fundamental research, and we can put them in chemical reduction of, say, graphite oxide into these ones that can be used in case of supercapacitors. We can use them as conductive inks and even battery electrodes, which we will explore a bit in this talk. So for large area graphene, for production for industrial purposes or other uses, we are considering two main techniques. So here we are looking at chemical vapor deposition, where we will use hydrogen as the starting material, operating usually at a maximum temperature of 1000 degrees. And you normally will have a substrate that we are going to operate with. In our case, we explore the use of copper, or in the case, we use also nickel. And the areas can be widespread. Then I'm going to also talk about the liquid phase exfoliation, where we use natural graphite, and this is done at room temperature, and we can have more than a meter size of substrate. In the chemical vapor deposition technique that we did, this work was done in partnership with my collaborators in the University of Pretoria in South Africa. What did we do? We tried to use chemical vapor deposition, where we pass the gas, and then we are able to degrade this gas. And then this is a very promising technique for large area production of graphene. It involves the dissolution of one or more gas species to be able to give your solid thin film. And as we show here, we have gases that we come in, and we are able to heat up to 1000 degrees Celsius, and we can produce our graphene. And the CVD technique is easily scalable, and it also offers compatible applications in industry. This is a typical one system that was used in our lab in Pretoria. We were able to produce our graphene on copper foils. Then these ones were also transferred onto various substrates. This is a one that has been transferred on the silicon SiO2 substrate, and we found some applications on what we can use this. When our graphene was produced on copper, we developed a technique called the bubbling technique, where we can peel off our graphene and be able to transfer this graphene from the substrate onto another substrate that we want to. So we can take from the metal catalyst and transfer onto glass, onto other substrates that we want, without sacrificing the metal catalyst that was used. So here shows a technique that we use, where we use the PMMA to coat on the substrate to hold the graphene that has been made on the copper. Then we use the bubbling, where we connect the electrodes with a steel electrode, and then it's copper conducted. What happens? We have hydrogen bubbles under, and we are able to lift, and we are able to do this transfer onto various substrates. So what do? We also explore the number of layers to be sure that we are within a graphene and not producing things like graphite. So we are able to identify whether they are single layers, bi-layers, or even when it is in multi-layers. So we explore techniques like Raman spectroscopy to be able to do this determination. And based on that, we still went further to explore imaging or what is known as mapping, to be able to study the quality of the films that were produced. And these ones were also explored in different applications. For instance, here shows the Raman mapping of the 2D band, which reveals the good uniformity of the grown films. And we can also tell something about the coverage that we have. Based on this, we explored the number of the time for deposition over a period of time to see their influences on. Of course, with the increase in the growth time, there was a corresponding increase in the number of layers, which shows the broadening of the 2D peak with time. For more details, you can see the literature that is already available online. We also explored using the scanning tunnel microscopy to see the structure of the graphenes that have been produced, and we can now use this for an application. For the dye-sensitized solar cell application, we explored the transmittance, and then we found some of its use in dye-sensitized solar cells. We tried on that, we produced some dye-sensitized solar cells with graphene as a counter electrode that has been produced from CVD technique. And in the case where the growth was about 20 minutes of deposition time, we're able to achieve about almost 4% of efficiency using the graphene that has been used as a counter electrode. We have also, the group has also explored the use of what is known as the graphene foam, which is a 3D graphene for the concept of supercapacitors based on other literature values that have been obtained. We have explored the use of graphene foam metal oxide composite. Here in the case, we have used hydrothermal techniques as well as the CVD technique, where we have aqueous chemical growth that has been done. We use also the manganese oxide with another technique called the successive ionic layer adsorption and reaction technique was also used in these depositions techniques. What we found out is that there are several advantages to these ones, meaning that there's an easy technique and then there's reproducibility, there's the reaction is carried out under moderate conditions. We also characterize them using Raman spectroscopy to also find the quality on the sheets that have been produced. Of course, the ratio of the intensity of the G peak and the 2D peak indicates few layers, and as we can see, there's the absence of the D peak, which indicates crystallinity with good quality on the films. We have also explored the porosity of this from even the scanning electron microscopy based on the nickel foam that was used. We also explored it in applications as an electrode material for supercapacitors. And here we showed the cyclic voltammetry giving us very good values. Indeed, here we have specific capacitance of about 305 at a current density of 1 Ag per A per G values that were obtained here. We have also explored these graphene foams also for other applications in energy storage, which is supercapacitors, using the graphene foam that is coated with manganese oxide. We use also 1 molar Na2SO4 as our electrolytes. We got quite good values of 240 farad per gram, and we have a maximum power density. Exploring these ones, we explored further and we found also the stability with no capacitance losses after about 1,000 cycles. So we have explored these ones in these techniques using CVD method. Now we went further with a group in Cambridge. We looked at the liquid phase exfoliation using ultrasonic assisted, what we call ultrasonic assisted liquid phase exfoliation to be able to produce graphene. And in this case, the graphene that was produced was used as printable graphene. So we do inkjet printing. We were able to also produce some inks from graphene using this technique, where density, viscosity, and surface tension is always an important value to consider. What do we do? Here we have graphite, and the graphite is placed in solvents depending on the different conditions. You can use water or we can use organic solvent. And we go through ultrasonication. At low power ultrasonication, we do ultra-centrifugation, and then we collect the top part, which is our ink, which I will explain to you. We use different surfactants like NMP, DMF, DMA, etc. can be used. And then we can also use water. But in the case of water, for various reasons, we have to use surfactant that we can explain. So as we see here, there's a dispersion in water and surfactant base. If you do that, the surfactant compensates the repulsion between the water and then the graphene. And the solvent, in our case, if it's an organic solvent, using the solvent with the right parameters will prevent the reaggregation and to be able to produce your ink. So we can produce these inks and then go on to high concentrations. We can produce 0.1 gram per liter, and we can also continue several times with iterations of the sonication and centrifugation to be able to come up with about 1 gram per liter. We can also improve the viscosity by adding some additives, and we have an ink. And this ink typically will typically be used as our ink for our inkjet printing. We have also studied the Raman spectroscopy of the inks that have been produced. What is quite interesting is that they showed there is a high D and D peaks here, which what we found out is that it's actually not coming from the graphene itself, but we see that it is localized disorder at individual graphene flake edges in the ink that has been produced because we exfoliate from the graphite. We have explored this ink that we have produced in inkjet printing technology. We put it in a printer that we can print various sizes. And in doing this, we have to take into consideration the ink parameters, including viscosity, surface tension, density, the influence that is going to have on the droplet sizes. These are important parameters, including even the size of the nozzle. The size of the nozzle of the cartridge in which we're going to put the ink is also very important. So we need to understand what is the principle behind. This is the several solid contents to be able to control these parameters. Then we do the check to see how the droplets are forming and how the droplets will be coming out of the cartridge. If it is this case, then we know that it is unstable. When we have a situation like this, then we have a stable droplets that are going to come, and we can have very good printability. This is a typical example that we did in the lab in Cambridge, that we are able to print on various sizes. So we can put in the cartridge, we can put in our ink into the cartridge, and then we can print. And we are able to print on flexible and even glass substrates, all kinds of sizes from 60 millimeters up to 20 millimeters. We can print 80 millimeters. We can go to different sizes. We are able to print about 300 millimeters, and we can also print circuits, etc., using this technique. So what we tried to do was to also put this application in a dye-sensitized solar cell, where we are going to replace our platinum. We try to substitute the platinum with the graphene and do printability of this ink that has been produced. So we did some printing, and here we have an inkjet printed graphene ink that was also tested, and we were able to come up with a dye-sensitized solar cell. And the interesting thing is we did this also using local inks that were produced from Ghana, and then were extracted from dyes, and then they were used also for the dye-sensitized solar cell. This is already online, and we can have more information on this. So this shows the application of the graphene that was printed and they used as a counter electrode. And we got it from these flowers that were locally produced. Pride of Barbados, we got from hibiscus sabdarifa, and then we made a comparison with retinizer N719 dye, and we got very good efficiencies here that prove that the technique that we have produced is workable, and then we are able to do our dye sensitizer and make a replacement of the platinum using this. So in conclusion, what do? We're able to produce these large films using the copper foil, using the CVD technique. We can also produce on nickel foam that is used as direct template for our synthesis. Electrochemical results show the composite exhibit improved pseudo-capacity behavior, which is very good. And in the case of our inks, our low-cost liquid phase exfoliated graphene inks exhibit promising electrocatalytic activity. And our study showed the possibility of inkjet printing graphene-based counter electrodes. And with this, I would like to acknowledge my group from University of Pretoria. The red one we had a sad news of him passing. So as he's here, I pay tribute to him. And the group here in Cambridge, they have supported me. I would like to acknowledge my university, University of Ghana, University of Trento in Italy, Cambridge Africa Program, the CAPREX, the Alborada Trust, the Banga Africa of University of Ghana, the Carnegie Corporation that made all these collaborations possible. I thank you very much for your attention.
Hey, David, thank you very much for the very nice and inspiring talk. Indeed, graphene has come a long way, and graphene for its application in solar cells has also come a long way. So I used to follow this literature long back, and I think some of your advances are truly remarkable in this area. Lately I have not followed this literature, but it was very inspiring listening to your talk. So that brings us to the end of the talks, but now we have another exciting thing in our program, which is the panel discussion. The panel discussion will be moderated by me, and then of course we have our three speakers, and then Alice is replacing Martin over here. And so I would like to start by talking a little bit about today's session. So today's session, as you see, we had speakers from three different parts of the world. And one of the main things that sort of came out of this, on what I think the speakers highlighted very beautifully in their talks, is that science is not constrained by material resources. Different parts of the world have different types of resources, and certainly, as the three speakers showed, it is not constrained by physical resources, but it is really the diversity of thought, diversity of minds, diversity of intellects that actually promotes and moves science forward. And so this is sort of the general or broad theme that we are going to try and maintain through this panel discussion. And hopefully the many interesting things may come out of it that will benefit early career researchers throughout the world. So with that, let me get started and maybe ask Alice if she has any opening remarks to maybe ask the speakers or to say something about the panel.
Okay, that's great. So Martin go for teaching, so I may place for him. Yeah, I'm excited for all these talks. Here are comments from the audience. He says that today is Volunteers Day. As a scientist, the most fashion thing to dating with science. I think that's true. We're really dating with science. Yeah, as Deepo said, was really right. This time we have three speakers from different continentals and different topics, but all related with the materials. All these materials and looks like that make very kind of inspiring way, especially for the most cheap way. like David was using inkjet printing, right? Yeah, and also this kind of simple process to make the very high, quality the sensors. Like Ludovico was, like $10, right? Yeah, so you need $10. And Zhuo was, PCB. As I have one question, so maybe I came to Ludovico first, okay? Yeah, so Ludwig, you research is very important because of food, right? Yeah, everyone needs this kind of basic materials. So you use our calendar just $10. So did you think everywhere in the whole world can get this, kind of cheap setup to do research in this way?
Well, the idea was to pretty much design the systems to be universally accessible. So one of the attractive aspects of Lego bricks, for example, that we ended up using for some of the our systems was exactly that it's pretty much universally accessible, and reusability was important, and all of these other aspects were important. I mean, I think the one of the things that I learned very quickly when I started working on plants was really the issue of scale and costs, because plants are very large. Experiments on biological systems require replicates, and plants experiments take weeks to complete. So the tools that you use to grow plants need to be extremely cheap. But at the same time, they need to be very reliable, very controllable. And so part of my work has really been to create this kind of what we call a glassware for biologists that really doesn't exist yet. And for chemistry, we tend to forget about how transformative was the invention of glassware in enabling chemistry to become a reproducible science. But I think in biology, as I pointed out, they have tremendous resources for characterization, but huge challenges in reproducibility of the growing of the organisms. So this is complicating the science and the analysis of data in these areas. So the cost is an enormous issue. At the beginning, for example, we were thinking of doing microfluidics, growing plants in microfluidic devices, and some people actually scooped us. People from Stanford, a group of Stephen Quake, scooped us very early on when I really started to do this work. And actually that turned out to be a blessing, because it forced me to reevaluate what it is that I was doing and why it is that I was using microfluidics. And as you see, a lot of the interesting things that you can get fluid dynamically from laminar flows, you don't need microfluidics for. Laminar flows can be obtained in millimeter scale or even centimeter scale objects. You don't need microfluidics for laminar flows. Mm-hmm. So a lot of things come from, I think a lot of creativity can be unlocked by refusing to go for the expensive solution.
Yes, and use a bricks, right?
Yeah, it's harder. And things that look simple are actually a lot more complicated than they look, from a point of view of the thought that went behind it. But it's, I think, very rewarding in the end. It's not necessarily universally appreciated in the scientific community, but it's extremely rewarding to be able to do something simple, spend very little money, use the money to pay your students instead of paying instruments, and and actually get very good publications out of that. So that's my point.
Super, yeah. So, Dave, maybe I can, just follow this question, go to Zhuo.
Sure.
Yeah. Zhuo Li, very nice talk for flexible electronics. I was, super interested in this because I'm working on this too. And how we are getting to one point, because everyone talk about the semiconductor. Always meaning expensive equipment, huge setups, clean rooms, all these things. So now we go to flexible electronics, like just Ludovico say that. Is that possible? We change something, by here to make simple, cheaper, to fabricate flexible electronics?
Yeah, I think the FHE is kind of a cheaper way, or a way that can eliminate the need for clean rooms, because we just buy those IC chips and then put it into the package. But of course, when we first go to this fabrication method, because my background is in packaging, well, although there are packaging people also do like clean room things for on-chip packagings, the very tiny interconnects for the ICs. But for part of us work on after the chips are already packaged into dies, and then we dice it and then putting them into PCBs. Well, and also I think for many of the young scientists and engineers, when we first establish our labs, some of us are fortunate to get the access to the very high standard clean rooms and very good equipment, but some of us may not have those success immediately. So I think just as Alice and Ludovic has mentioned, that maybe use this brain and then find some collaborations and find some interdisciplinary areas that you can work on with the resources that are acceptable to us, that is also possible. Actually, I want to just say something about Ludwig's work, because I was very surprised about this work. It's very interdisciplinary. I was first to think about how could the material scientist be related to food. I was thinking maybe some biomass plastics, biomass energy, that's also a hot topic. And then I found his hydrogels that is used for grow plants. Yeah. And actually, when I was a PhD student, and I had a conversation with my husband. He is also a scientist, but he is working on mechanics. So we were talking about how amazing those plants' roots can grow into the soils, because it's very tiny, but the pressures and also the conditions are not very easy for them to grow. And then they grow into those structures, they divided, and it's just like a fracture, like the fracture in our material science, how the fracture grows and propagates. So we were talking about how could we maybe observe how they can grow. So we out of our curiosity, we bought a glassware just to put the soils in, and then put the roots, and we observe for some bit. We did not finish. I cannot get a very good conclusion. But when I saw your research today, I think, oh, we can do research like this, because I'm also working on some hydrogel work that I didn't present today, but that was for flexible and wearable electronics purposes. But I haven't think about, you can put them in to observe the growth of plants. So I think as long as you can use your imagination, you can put all kinds of disciplines together. So maybe you think, that's something that's none of my business. It's not within my research interest. But when you talk with people, it's, you can do something together. So I think that is also an area that may not need maybe a very good equipment, very high standard environment or something, but just talk with people maybe in your area. Well, most of the times out of your area, and you can find some multidisciplinary, interdisciplinary work that has not been found or researched before. So I think that's what I thought when I watched your slides. I think, that's very interesting.
That's great. There's a lot of cross-fertilization of ideas you can get by listening to other people's talk, especially from different disciplines. I guess that's the main purpose of iConnect talks and what it has enabled all over the world. So, given that we are on this note, let me ask the David about a more broad or general question that all of the panelists, but particularly the David, you have worked across variety of continents, right, in Europe and in Africa, and you have seen science happen in a variety of settings, right, all the way from Cambridge, UK, which is has very resourceful, very well established, also in Germany, France, and then also in Africa. Can you comment on how differences in resources, right, physical resources in different areas, and maybe also compare differences in sort of intellectual resources and how those gaps are filled in different places that you are able to do such wonderful science by pure willpower determination, even though the resources may not be the same as compared to, say, Cambridge with in Ghana, for example.
All right, thank you very much. That's perfectly true. Getting trained for the PhD in Italy, traveling all over the Europe, working in sophisticated laboratories. I worked in the synchrotron. I did all kinds of research. Then it got to the time where I have to come back to Africa. I came back to Ghana, and where, of course, you don't have all those scientific facilities available to you. It's either you decide not to do anything and get perished and you don't get known, or, as we say, you have to find whatever strategy that you can use to survive, and you have to keep your head up. The best one that I saw that I want to pass on to those listening to us is, it's not only where you are, but wherever the resources are, and then you have the brain to be able to do that. So I leverage on my networks to be able to go. So it was at a conference, then I met this Professor Manyala that is on here listening. At a conference, we were just having a discussion. I was about defending my PhD, whether I should go or not. And he said, okay, I have this lab. We are also young. We can find something to do together. I come to Ghana. We make all the necessary arrangements. I fly down to South Africa, and it made a lot of change. Interestingly, that graphene was not even my PhD work. I worked on nanostructured copper oxides for environment and energy applications, which were quite similar. Then I got into this group as a postdoc to now learn about a new material, because the group works in carbon technology. I mean, I'm putting this across because once you finish your PhD, and as a materials person, you can have a lot of diversity. It's not, I'm working on only this one and I can't do it. And we work perfectly. That was where I learned about the CVD. I learned about all those techniques. And you can find that University of Pretoria was really, and it's really well resourced. And that gave me some leverage. And we were able to produce graphene for the first time by ourselves. We're three of us. We were able to produce, and I remember vividly when we did our CVD and we landed in that, we said, it's not only the Scotch method, which we were doing, but we can actually produce this. And this took us to another level, built our level of confidence. We had access to some facilities that led us to go to some collaborators in Germany. Now we can do very good science with partners. We got partners in the US, we got partners elsewhere. Right after South Africa, I came back to Ghana. Then there was this postdoc with what is known as the Cambridge Africa Partnership for Research Excellence, where we can now link up with high region like Cambridge, and interestingly, to work with the Cambridge Graphene Center, right, which was high. And this gave me a lot of leverage. Got in to be able to use clean rooms, which is not available, and to be able to do high quality science. And this gave me a bigger platform, going to carbon conferences, meeting more networks, and these papers went on and on and on. So it's not only what you can find in your region, but you can use your mind. Based on these travels, I was able to build my own lab and to set up my own group. And we are able to do this quality science, and we explore from here. And some of the quality ones still happen. And I believe strongly in collaboration across the world. And I think this is how we should go. We should not say we are under-resourced and then we cannot do it.
No, that's
Wow.
very noble thoughts, and very appropriately said that the resources should not restrict you. And you also said something that resonated with me quite well, that material science is a very broad science. Once you get trained in materials, you can really work across disciplines. And I am also a trained material scientist, so I can certainly attest to that statement that David made. So let me also focus on some other aspects of what not only David said, but which is common. That not only that all the three panelists have diversity in geographic research experiences, but also all of their research is extremely interdisciplinary. They cross boundaries, right? As David was just mentioning. And so this is actually a comment that Martin left with me before he had to go to teach, which is, you have a lot of the sort of disparity in the resources available, for example, but even the research itself is so different, right? And it brings in elements from so different parts or different parts of sciences. Like, for example, the Ludovico's research, material science with plant science and photonics, and then mass transport, right? These are extremely different disciplines. You don't There is also an important ingredient required for all this, which is a diversity of cognitive and intellectual thought, right? The diversity of intellect, diversity of cognitive thought, right, is very important. How do you incorporate that into your research? Is it through hiring students, or do you yourself read the different papers, or the papers from very different areas, or books, or travel to conferences outside your field? What do you do? Maybe Ludovico can first take a stab at this.
Yeah, my my let's say approach is kind of maybe different and unusual in a sense. And my approach actually comes from reading as little as possible, because the tendency reading papers is something I do after the work is done. So reading the papers tend, as my advisor in Boston used to say, it tends to color your thinking. So of course, if you it depends on what kind of science you do. So in my approach is to usually go far out of my comfort zone, where I know literally almost nothing, but using a know-how that hasn't been employed in that area, and start asking questions, start the first most basic questions. And so usually what I find is that those very basic questions are very often questions that those specialized communities actually don't have clear answers for. They've actually forgot about, and or they've given up on, because maybe they don't have the tools to answer them. And so sometimes, usually often, you find that those very basic questions are still open to inquiry. And that allows you a very easy enter, or relatively easy enter into a new field, because you are going for some very basic questions that have been abandoned. But you have a new set of tools to bring to that research. And so that gives you the opportunity to do something where you don't have competition, where you don't have to have very an extraordinary expertise, but where you can have a dramatic impact on that field. So that's at least is what I've tried to do, and I think it works. It works reasonably well, and you have the advantage that you don't have to spend an enormous amount of time reading papers.
Oh, that's
Why
a very wise
exactly?
advice.
Yeah.
Alice, sorry, go
Yeah.
ahead.
So I mean, Ludovico's answer was exactly, try to, coincidence with Zhuo's, comments. You think about, how the plants grow, right? Yeah. How else to get to that? So we get to the right point. So everyone asks that question in their mind, but no one has a tools, right, to see that equipment. So you found your way, you can solve the problem. That's a new field. Yeah. Yeah, that's a new field. This very good. I think Ludwig, you use your brain too much. Yeah, always very hard here. So you lose all hairs, right? Yeah.
Yeah, I know.
But this is a very wise
That,
advice
you're,
from
you're a
me.
young scientist. I try to
Yeah.
explain why you lose the hairs, right? Okay. Yeah, Zhuo.
So
Yeah, like a deep question. How you get to this new, interdisciplinary field? Yeah.
I think for me it's relatively simple. I just go to a conference. So yeah, I think as Alice has been working on this for quite long years. It's stretchable electronics itself is a multidisciplinary area. So when I attend the conferences in the area, we have not only material scientists but different engineering disciplines, mechanical, electrical, computer science, and also some medical area professionals will attend. So just talk to them. And also, you will find that a lot of areas are interconnected with each other. So when you work with electrical engineers and then you find something that maybe they are interested and I'm interested, and we start to collaborate. And one of my collaborators, Professor Ya Jieqing, he is a professor at Fudan University, but I never met him before. And then we attended the same conference, and then we get to know each other. And then we find out, okay, oh, so I never know you on campus. And after that, we start to talk our research. And his specialization is IC design, but he's also interested in those kind of stretchable wearable electronics, but from different aspects. So we start to talk and then get collaboration. And I think up to now it's almost 2 years. And so for me, I think that's just go to different conferences and just talk to different people. We give fresh new ideas. I think, as I just mentioned, Ludovico just refresh my mind again. So I was asking myself, I was asking myself, when I have time, do I want to do that experiment again to see the root growth or something? Although it's not my major research area, but sometimes out of curiosity, if I have time, maybe I can do this experiment, maybe with my kid at home. Just to
That's
find
where
something.
innovation come, Yeah, that's where the new science come. I think you should try. Now you have a good partner. Deep. That's exactly why we want to host this, right? Yeah, we got the people inspire each others.
Yeah, actually, I ended up getting some new ideas over here. I spent too much time reading papers from all over the place.
Okay.
Maybe I should do like Ludovico. Just find an area that I'm curious about. Just go there without knowing nothing, and then start poking around, and maybe I'll come up with as creative ideas as Ludovico does. So thank you for that.
Remember your hairs. Okay, now you have a full, very good hair shape. Yeah, later you are all this. Okay. Yeah, Didi. Okay, come to you. You got so good, connection network, and growing so good. Your career was developing very good now. So is that really depends on many language you can speak? The communication skill. Can you share with us? Because I think many young scientists need this. When you go to conference, talk to others, how can you, get the connection?
And I go to conferences and I talk to people, but taking it back to what Ludovico Zhuo talked about, I don't only go for the conference. I go for conferences to get those ideas, but here actually I also get a lot of those ones from the local problems that we have. We tend to have a lot of challenges that we tend to find more solutions that are adaptable to the local situation than in elsewhere. So usually I try to find a balance between doing blue sky research and doing research that is really local. I mean, doing those ones with your students. And most of my recent research have been driven by the local challenges and then for students. For instance, I do circular economy, which I didn't present here. We do plastic waste conversion into fuels. We do all these ones in a circular economy. Why? Because this is real challenge that I see every day. How do we find solutions to, say, plastic waste? There's flooding, there's agricultural waste. Can we convert that one? So I find that particular link. For instance, in the case of the supercapacitors, I do something that we can convert the plastics. You still have carbon that is remaining, and this carbon can be put into a supercapacitor. It can be produced into battery. And this extends the level of what we can do. I can extend to food. Can I go into agricultural waste? Okay, so I see these ones even in conferences and I have these various discussions. Sometimes when I go for conferences, well, I need one or two languages just for communication and then make the approach. And getting those networks in conferences are very, very crucial. We don't go there and don't only listen to presentations. The networking, when it is during the break, whom am I talking to? Maybe the person even presented something that is not in my area. But after talking to the person, this person is more connected than what the person even presented. And we take it up from there. So there are a lot of local issues that we are doing, research that is going on, that I still have international collaborators that possibly are doing the blue sky, but I try to bring the blue sky to midway to help solve national problems. Okay, that is more relevant to our people here, and we can still get good publications out of it. You know, because of those collaborations that I have, I can take my sample to a place where, for instance, if I don't have a very sophisticated equipment, this can be done out, and then we can get the results, and we can still get published. So
That's
this
amazing.
is where I'm. Yeah.
No, that's really what you have given us is new insights into how to work in constrained environments, but across the chain, all the way from basic science to applications, which is rare to find. Not always do you see these kind of approaches taken to science. So very, very grateful for that. So I would like to tell to the panel and all the listeners that we have hit more than the 2 hour mark. So I think it is time where we conclude. And here in the United States, our day is just getting started. So we have to move on to other parts of our daily schedule. But let me remind everybody over here that these talks will continue all through the year. And please attend next Tuesday, which will be the first session of the youth talks of the Chinese version on February 21, which is next Tuesday. And once again, you have an exciting lineup of speakers over here. In fact, I recognize a couple of speakers over here. One of them was my former colleague. And so please do attend these talks. They would again be very exciting. And come back for the English talks on February 28th, which is 2 Tuesdays from now, or the Tuesday after next Tuesday. So with that, I would like to thank everyone for attending these talks once again. Thank you to the amazing speakers we had for giving very enlightening, interdisciplinary and exciting talks and sharing their wisdom on how to do science across disciplines and also across geographies and across various constraints or sort of advantages in sort of resources available for doing science. So once again, thank you all very much. Alice, do you have any final comments you want to make?
Oh yeah, congratulations for everyone today. The opening will have a 21,000 audience online. Yeah, that's super. I think now we have more connections. Yeah, we got all these ideas well out. Proud of all of you.
Thank you all once
Okay,
again.
yeah, great.
Take care.
Okay.
Bye-bye.
Bye.
Thank you.
再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can